can check it to make sure the assumption is correct, but let's make that assumption. So the assumption is that D1 turns off after the peak. So after this peak, the diode turns off. So if the diode turns off, what do we have left? The diode is not here. We have one capacitor, one resistor. The voltage across the capacitor is still as before, 2V0 minus VD on, like here. So this circuit can be simplified to something we are very familiar with. The circuit can be simplified to one capacitor having a voltage on it equal to V0 minus VD on, this voltage here, this voltage here, this voltage, V0 minus VD on, the peak value minus 1 diode drop. And this capacitor is connected to a resistor. So as you remember from basic circuit theory, if you have a capacitor that is charged and a resistor is connected to it, the capacitor voltage, which is the same as the resistor voltage, will decay exponentially. So what we would expect this voltage to do is V out. I will draw it here for now, and then I'll bring it back to the main plane of waveforms. As a function of time, V out goes like this. So that's V out of that little circuit here. This is what we know from basic circuits. Okay, so the same thing should happen here. The diode has turned off. We have a capacitor with that much voltage. We have a resistor. So from here on, it's not a sinusoid anymore. It's a decaying exponential. So it exponentially decays. I deliberately made this decay very slow. We will see why. So that it just gradually is losing charge, the capacitor through the resistor, and gradually coming down. Okay. Now, what is the input doing in the meantime? Well, the input keeps going down, going negative. The diode is still off. That was our assumption. The diode is off, the diode is off, the diode is off. Now, let's look at this point. At this point in time, the output voltage has decayed. The input voltage has come back up. And they happen to be equal. This voltage happens to be equal to this voltage. Does the diode turn on? Not quite. If we use the constant voltage model, we need this much voltage for the diode to turn on. So not yet. Now we have to let the input go up, the output to decay, until the difference between these two in this direction is sufficient to turn on the diode. So when this is sufficiently more positive than this, one diode drop, the diode turns on. So diode turns on right here. So D1 turns on again. So maybe I should write here as well. D1 turns off. Well, I guess I wrote it before, so I don't need that. But anyway, D1 turns off. Okay, D1 turns on again. Now, if D1 turns on again, what does the circuit look like? Here's what we have. We have a voltage source, VD on, a battery, and V in, a sinusoid that's going up, and the capacitor again. The voltage on the capacitor is about input minus VD on. So at that point in time, we have a situation where the input is some amount, we have VD on here, and the voltage on the capacitor happens to be this voltage minus VD on. That's when the diode turns on. So now what happens? Well, again, the output is pinned to the input. So the output continues to track the input. We track the input. Up to what point? Up to the peak. We reach the peak. At the peak, we still have V in minus VD on across the capacitor. And then once we go past the peak, the diode turns off. So we have another decay afterwards. In other words, this waveform from here, this waveform from here to here, and from here to here, repeats. We decay, then we charge the capacitor again, then we decay, then we charge the capacitor again, and so on. That is the output waveform of the half-wave rectifier in the presence of a load capacitor and a load resistor. All right. The waveform that is generated here instead of the constant DC that we produced before is called a ripple. So this is called ripple. We say we have ripple on the waveform. Ripple is like what you see on the ocean, the waves, small waves. So we have a ripple here. The question is the ripple a good thing or a bad thing? If it's a good thing, we want to make it larger. If it's a bad thing, we want to make it smaller. Well, what this means is that what we thought was a nice constant voltage given to our electronic device is actually not constant. It fluctuates. So that fluctuation is undesirable. In some cases, very undesirable. I'll give you a quick example. Let's suppose that you have some sort of audio device, like an MP3 player or a radio or something. So imagine that you have a charger that is charging a radio. Okay, so you're listening to the radio, and at the same time you have plugged this into the wall, and this is the DC, presumably the DC, this DC. But when it connects to the device, to the audio device, because the audio device draws a current, we have ripple on this voltage. So then what happens? You will hear a humming noise in the background of the music that you're listening to. And that humming noise is because the supply voltage that's coming to the device is not constant. It keeps going up and down at a frequency of, for example, 60 hertz in US or 50 hertz in other countries. So that is a problem. The ripple must be minimized. Well, now the question we have to ask ourselves is, how much is this amplitude of ripple? From this peak to this valley, how much have we lost? We have to calculate that. Once we calculate it, we see how it depends on the various parameters of the circuit. And from there, we can decide how we should reduce the amount of ripple, how we should suppress this effect. All right, so how do we calculate the ripple? It looks a little complicated because we have a nonlinear circuit, we have part of a sinusoid, then an exponential decay, and so forth. So it doesn't seem to be straightforward, but we can make some approximations. The approximations are as follows. We know that this circuit is presumably well designed, which means its ripple has to be small. Okay? If the ripple is small, it means that this decay is very slow. It starts from here, it decays very slowly, and touches here, and then again. So for the ripple to be small, the decay has to be very slow, so that we don't lose much charge from this capacitor when the diode turns off. All right, so if the ripple is slow and small, then we can draw two conclusions. Conclusion number one, if the ripple is very slow and small, what happens is that the diode turns off here, and it turns on around here. It turns on very briefly. And that makes sense, because if we didn't take much charge out of this capacitor by the laptop, we don't need to provide much charge to it in the next cycle. So the diode turns on only briefly here, if the ripple is small and slow. So what I can say is that this decay lasts about one period of the input. It starts from here and lasts about, not completely one period, but close to one period. So I will write that down here. That's a very important assumption that we're going to make. So if the ripple is small, then decay lasts about T in. And T in is the period of the input. So for example, it's easier if I show it here. So T in is from peak to peak, one positive peak to the next positive peak. So here's T in, or from one zero crossing to another zero crossing, from here to here, or from here to here, etc. That's T in. So we can say that from here when the diode turns off until the diode turns on again is approximately T in. This is only true if the ripple is small, and the ripple has to be small for this design to be a good design. If the ripple is large, then we'll have lots of humming noise in the audio device example I mentioned, and then it's not a good design. Okay, so if that's the case, we can assume that this decay lasts about T in seconds. If the frequency of this voltage is 50 hertz in other countries, then T in is 20 milliseconds. If it's 60 hertz like in US, then T in is about 16.7 nanoseconds, 16.7 milliseconds, right? So those are the numbers that we can keep in mind. All right, so we made one assumption so far, that the ripple is small, hence the decay is slow, and therefore the time from here to here is approximately